Hello everyone, I will be explaining the chapter Noise in Continuous Wave Modulation Systems. Following are the contents: noisy receiver model, noise in DSBSC receivers, noise in SSB receivers, noise in AM receivers, noise in FM receivers, and lastly the pre-emphasis and de-emphasis in FM. In this session, I will be covering noisy receiver model and the noise in DSBSC receivers. Figure shows the general block diagram of the noisy receiver model. S of t is the modulated signal that appears at the input of the receiver. W of t is the noise that gets added during the transmission in the channel. The first block in every receiver model is a bandpass filter which selects the desired station while rejecting all other frequencies. Mainly it has a tuned circuit for this purpose. Demodulator demodulates the signal to get back the original information. Assumptions. Some assumptions are made before going for the calculation of the performance of the various types of receivers. The noise. The noise is considered to be a additive white Gaussian noise having a constant power spectral density of N0 by 2. The noise is said to be additive as it gets added to the signal. It is said to be white because it is having a constant power spectral density of N0 by 2 and it has a Gaussian distribution function. Bandpass filter. The bandpass filter is assumed to be ideal, having a bandwidth equal to the transmission bandwidth of the modulated signal and has a midband frequency same as that of the carrier frequency Fc of the modulated signal. Plot shows the frequency response of the ideal bandpass filter. It has a center frequency Fc and having a bandwidth equal to Bt. This bandwidth Bt is equal to 2W if it is a AM or DSBSC and it is equal to W if it is SSB. Narrowband noise. White noise after passing through a bandpass filter, it is called as a narrowband noise. It has the in-phase and the quadrature phase components represented by N of t equal to Ni of t cos 2 pi Fct minus Nq of t sin 2 pi Fct. Plot shows the PSD of the white noise, frequency response of the bandpass filter and PSD of the narrowband noise. This PSD of the narrowband noise is the product of the PSD of the white noise and that of the bandpass filter. Measurement of performance. There are three types of SNRs defined. Channel signal to noise ratio SNRC is defined as the ratio of average power of the modulated signal to the average power of the noise within message bandwidth, both measured at the input of the receiver. Input signal to noise ratio SNRI. It is defined as the ratio of average power of the modulated signal to the average power of the filtered noise, both measured at the output of the bandpass filter, that is at the input to the demodulator. Output signal to noise ratio is defined as the ratio of average power of the demodulated signal to the average power of noise, both measured at the output of the receiver. In this block diagram, at this point, that is at the input to the receiver, SNRC is measured, at the input to the demodulator, SNRI is measured, and at the output of a demodulator, SNRO is measured. Figure of merit of the receiver. It is defined as the ratio of SNR output divided by SNR at the channel. Higher the value, better is the performance of the receiver model. Now, we will go for the performance of DSBSC receivers. Figure shows the general block diagram of the DSBSC noisy receiver model. The first block in every receiver model is a bandpass filter. In the coherent detection of DSBSC, we have a product modulator followed by the low pass filter. In this, S of t is the modulated signal, which is a DSBSC signal. W of t is a AWGN noise having a PSD of N0 by 2. The received signal is Z of t equal to S of t plus W of t. As we are dealing with DSBSC, S of t expression is CAC cos 2 pi Fct M of t plus W of t. Now we'll go for the calculation of SNRC, which is the ratio of power of the modulated signal to the power of the noise within message bandwidth. Now let us see the expression for power of the modulated signal. The signal component in the received signal is CAC cos 2 pi FCT into M of t. Average power of this signal component is expectation of S square t, which is equal to expectation of CAC cos 2 pi FCT M of t square. If we evaluate, we get the expression as C square AC square by 2 into P, where P is the power of the modulating signal M of t. Now we'll go for the calculation of average power of the white noise within message bandwidth W. It is given by the integration of S of f df within the limits from minus W to plus W. If we evaluate the area under the curve, we get N0 by 2 into 2W equal to N0 into W. Therefore, SNRC is the ratio of average power of modulated signal to the average power of noise within message bandwidth, both measured at the input of the receiver. From 2 and 3, the expression for SNRC is equal to C square AC square P divided by 2 N0 into W. Next, we will go for the calculation of SNRI. It is defined as the ratio of signal power to the noise power, both measured at the bandpass filter output. Now let us see the expression at the output of the bandpass filter. It is x of t equal to s of t plus n of t, where s of t is the DSBSC signal and n of t is the narrowband noise. Now average power of the signal component is C square AC square by 2 into P. Average power of the filtered noise is P equal to Sn of f into df, which is the area under the curve of Sn of f. If we evaluate, we get the power as Bt into N0. As Bt is equal to 2W for DSBSC, so therefore average power of the filtered noise is 2W N0. SNRI is the ratio of average power of modulated signal to the average power of filtered noise N of t. From 6 and 7, we get SNRI as C square AC square P divided by 4 N0 into W. Next, we will evaluate the SNR at the output. The output of a bandpass filter is given to a product modulator. Now we will see the expression at the output of the product modulator is represented by V of t equal to x of t into cos 2 pi FCT, where x of t is a signal plus the narrowband noise into cos 2 pi FCT. If we simplify, we get the expression as given in 9. It is observed that the second term is centered around 2fc, third term is also centered around 2fc, whereas the first term is within the bandwidth W. Therefore, the low pass filter output is y of t equal to only the first term half CACM of t plus Ni of t. Out of this, the signal component is half CACM of t. Therefore, average power of this message component is half square C square AC square into P, which is equal to C square AC square P by 4. Now let us go for the calculation of the average power of Ni of t. The noise component in y of t is half Ni of t. As we know, the PSD of the narrowband noise N of t is equal to N0 by 2 within the bandwidth Bt. Then PSD of Ni of t equal to Nq of t is given as shown in the plot. This is using the property Sni of f equal to Snq of f equal to Sn of f minus Fc plus Sn of f plus Fc. If we delay the Sn of f spectrum by Fc units, advance by Fc units, then add the two spectrums, we get the spectrum of, that is SNI of F and SNQ of F. If we calculate the average power of this SNI of F and SNQ of F, it is equal to 2W N naught, which is equal to area under the curve, N naught into 2W. Therefore, average power of the noise component at the output of the receiver is half square into 2W N naught, which is half W N naught. SNR at the output is defined as the ratio of average power of the demodulated signal to the average power of noise, both measured at the output of the receiver. From 10 and 11, we get SNRO equal to C square AC square P by 2W N naught. From 4 and 12, figure of merit of the receiver is SNR at the output divided by SNR at the channel equal to 1. Now, we will see the summary of the performance of the noise in DSBSC receivers. We have the modulated signal S of t equal to C AC cos 2 pi FCT M of t. The noise at the input of the receiver is W of t. Bandpass filtered noise is a narrowband noise. Average power of the DSBSC signal is C square AC square by 2 into P. Average noise power within message bandwidth is W into N naught. Therefore, SNRC is average power of DSBSC signal divided by average power of noise within message bandwidth equal to C square AC square P by 2 N naught into W. Average noise power at the bandpass filter output is equal to BT into N naught. Since BT is equal to 2W for DSBSC, it is equal to 2W N naught. And the receiver output, we have seen the expression as CAC M of t plus NI of t whole divided by 2. Average power of the message component is half square C square AC square into P. Average noise power within at the output of a bandpass filter is N naught into W by 2. Therefore, SNR at the output is C square AC square P by 2W N naught. Finally, the figure of merit is SNR at the output divided by SNR at the channel equal to 1. In the next section, we will take up the performance of noisy SSB receiver and noisy AM receiver models. Thank you.